Thousands of kilometers of massive steel oil pipelines lie submerged and silent along the vast seabed of Saudi Arabia. These structures represent a critical infrastructure network for transporting the energy that sustains the entire global economy. Why would engineers choose to place thousands of kilometers of steel pipelines beneath these specific desert seas? The answer remains hidden deep beneath the ocean floor, where the intense flow of energy begins its primary journey. It only looks obvious to transport oil via tankers, but in reality, the underwater environment provides a stable, continuous route that avoids the congestion and risks of surface shipping. Everything only gets more complicated when considering the scale of the operation. Since the early expansion of the oil industry in the Middle East, Saudi Arabia has constructed extensive offshore pipeline networks to move crude oil continuously and safely from distant offshore fields to onshore processing facilities and international markets. But this is just the beginning. Installing these heavy pipelines beneath the ocean surface posed enormous engineering challenges from the very start. One can notice how the equipment gradually lowers the steel sections into the depths with the hiss of massive hydraulic tensioners. The process is only gaining momentum as specialized vessels maintain their position using satellite navigation systems. It is visible how the protective coating on the steel pipes glints under the industrial lights before they vanish into the dark water. At first glance, laying a pipe seems like a simple task of placement, but in reality, every meter requires precise calculations of buoyancy and structural stress. The heavy steel lays in an even layer on the prepared seafloor, guided by automated systems that monitor every centimeter of the descent. Transition to the next level. The material is ready to move to the next processing phase without haste. $100,000 or more is the annual salary often reached by workers in the high-stakes sector of petroleum extraction. Why do these laborers receive such significant financial compensation for their efforts? The answer lies in the extreme physical toll and the constant danger inherent in the environment of offshore rigs and deep subterranean wells. But this is just the beginning. It seems simple to associate the industry with a famous political slogan, but in reality, the phrase "drill, baby, drill" represents a fundamental economic necessity for the stability of the United States. Oil functions as the primary lifeblood for the modern global infrastructure. The process is only gaining momentum. One can notice how the reach of this resource extends far beyond the fuel tanks of airplanes, ships, and automobiles. Petroleum serves as the essential raw material for the production of plastics and the synthesis of complex chemicals across thousands of industrial sectors. It is visible how the entire global market reacts to the slightest shift in the price per barrel. Because a minor fluctuation triggers an immediate chain reaction, transportation costs climb, inflation accelerates, and the cost of consumer goods rises for millions of families. At first glance, the system appears robust, but in reality, the daily lives of citizens remain tied to the continuous flow of this liquid energy. Everything only gets more complicated when considering the human cost of maintaining the supply. 12 to 13 hours is the standard duration of a single shift for those stationed on drilling platforms. The equipment gradually vibrates with intense mechanical force, creating a loud and demanding atmosphere that never ceases. Workers spend many consecutive weeks isolated from their families to ensure the drills continue to penetrate the earth. One can observe the heavy manipulators and hydraulic systems moving with calculated precision amidst the constant risk of catastrophic equipment failure. Fatal accidents and sudden explosions remain a persistent threat that the crew must manage every minute of the day. The camera glides along the steel structures where every bolt and valve is under immense pressure. Thus, the massive resource supply is maintained through a combination of extreme environmental conditions and rigorous human labor. The oil flows from the depths into the transport systems, and the cycle of production concludes this phase by securing the energy needs of the nation. 200,000 steel oil pipeline sections. This was the volume required for the initial stage of the project, where every unit had to meet rigid accuracy and quality standards. Why was such a staggering quantity of material produced with such extreme precision? One might assume a standard industrial tolerance would suffice for a pipeline, but in reality, the harsh offshore environment and high operating pressures leave no margin for error. This necessitated a massive logistical operation that utilized the full industrial capacity of 3 major manufacturing plants mobilized across Saudi Arabia. These facilities operated 24 hours a day to maintain a production rate of nearly 100 oil pipeline sections every 24 hours. Each segment was fabricated from high-strength steel plates engineered specifically for structural resilience under deep-sea conditions. The process is only gaining momentum. One can notice how the equipment gradually rolls these flat plates into cylindrical forms before a longitudinal weld is applied along the entire seam. 1,150 millimeters is the external diameter of each section, with lengths reaching up to 12 meters. After welding, the pipes undergo hydraulic expansion to guarantee that the dimensions and roundness are perfectly uniform across the entire batch. It seems like a simple mechanical stretching, but in reality, this ensures the structural integrity of the cylinder. The pipe ends are then beveled, creating the precise geometry needed for welding during the offshore installation phase. Every single pipe segment is subjected to a comprehensive quality inspection protocol before it can be cleared for deployment. Non-destructive testing is used to verify the weld seams, ensuring that the structural reliability of the steel remains absolute. It gets more complex further on. Because the metal must survive decades underwater, the application of protective coatings becomes the primary focus of the fabrication cycle. Multiple layers of specialized materials are applied to the steel to preserve its strength and enhance internal flow. One can notice how a low-friction epoxy lining is sprayed onto the inner surface of each pipe. This reduces the resistance encountered by the crude oil, minimizing pressure losses across the vast distances of the offshore routes. It only looks like a smooth finish, but in reality, it is a critical factor for maintaining the efficiency of the entire transportation network. Simultaneously, the outer surface receives a specialized external polymer or epoxy anti-corrosion coating. This layer serves as the main defense against the electrochemical reactions and chemical corrosion triggered by the aggressive seawater surrounding the oil fields. These protective systems work together to extend the operational lifespan of the infrastructure. Transition to the next level. Once the fabrication and the concrete weight coating are finalized, the logistics of transport begin. Specialized transport vehicles and barges are required to move the pipe sections, which weigh several tens of tons each. Coordination between the manufacturing plants, storage yards, and coastal ports is maintained with jewelry-like precision. One can notice the heavy cranes and handling systems lifting the pipes in the storage yards, where they are organized according to a specific installation sequence. The equipment gradually positions each segment to minimize impact and prevent any damage to the outer coatings. Supply vessels and offshore pipeline vessels receive the material from these coastal transfer terminals according to a strict schedule. This constant flow of components ensures that the offshore installation process remains uninterrupted and steady. The heavy steel sections are secured for the sea journey, moving from the yard to the final site of deployment. Thus, the steel reaches the standard ready for the further stage of the project. 24 tons is the approximate weight of a single section of oil pipeline before it enters the assembly sequence on a specialized vessel. Why is the entire deck of such a ship designed as a closed-loop industrial line? It would seem that assembling segments in a stationary port would be more stable than working in the middle of the sea. However, performing every installation step continuously offshore allows the vessel to function as a mobile factory that never stops its forward momentum. The process begins when two massive sections are positioned for welding and meticulously aligned to ensure a perfect geometric match. But this is just the beginning. Automated welding systems execute a full circular weld around the pipe circumference with mathematical precision. One can notice how inspection equipment immediately scans the finished joint to detect even the smallest defects or potential leaks. Only connections that meet 100% of the strict technical standards are permitted to move further along the deck. A dedicated protection system is then applied to the welded joint, combining heat shrink sleeves with flexible filler materials. This barrier prevents corrosion while allowing the steel to adjust to the uneven terrain of the seabed without compromising the seal. Everything only gets more complicated as the vessel slowly advances along the planned route. The connected pipe sections are continuously guided into the water and gradually lowered into their final position. This requires precise coordination between the transport, installation, and positioning systems to manage the tension. 3 kilometers of pipeline can be installed in a single day using this method. Such a speed is rarely achieved in the demanding world of offshore construction. Transition to the next level. Engineers must overcome significant geological and marine environmental challenges through careful seabed preparation. At first glance, the ocean floor appears uniform, but in reality, it is a complex landscape requiring constant management. Specialized support vessels operate ahead of the main installation fleet to address sections where the seabed is uneven or rocky. One can notice how these ships fill depressions with rock and gravel to create a level and stable base. This prevents the pipe from spanning gaps that could lead to structural fatigue. The pipeline could not simply rest on the seabed in shallow water zones exposed to strong waves and powerful currents. The process is only gaining momentum. In these areas, the pipe is installed inside pre-excavated trenches that are later backfilled to provide permanent security. The route also intersects with existing subsea infrastructure like power lines and communication cables. At these crossing points, protective rock berms are constructed to shield each independent system. This ensures the structural stability and long-term reliability of all infrastructure sharing the seabed. The installation process concludes this phase, opening the road to final commissioning and operation. The pipeline rests securely on the ocean floor, ready for decades of service. Millions of years have passed since ancient sediment layers beneath the crust of the Earth first began preserving the vast reserves of oil and natural gas that now sustain modern civilization. Why are these energy resources so difficult to extract from their original geological traps? Most of these productive oil fields are not situated beneath accessible land, but instead remain hidden thousands of meters below the floor of the ocean. The solution to this geographic challenge was the engineering of massive machines known as offshore oil rigs. Construction of these industrial cities begins on land within specialized shipyards. Gigantic steel structures weighing tens of thousands of tons take shape before specialized heavy lift vessels transport them across the open water. One can notice how the equipment gradually moves these steel giants toward their final extraction coordinates. Fixed platforms reach the site and begin the process of stabilization. Enormous steel legs descend through the water column to be driven deep into the seabed. Once anchored, these legs are reinforced with concrete to ensure they remain stable in water depths ranging from 60 to 120 meters. But this is just the beginning. In remote offshore regions where the ocean reaches depths of several thousand meters, engineers must rely on semi-submersible drilling rigs. These structures maintain their stability through the use of massive floating pontoons positioned carefully beneath the turbulent water surface. It only looks obvious that a floating structure would be unstable, but in reality, anchoring systems made of chains stretching for thousands of meters allow for safe operations. These systems function at depths of up to 12,000 feet, a distance approximately 12 times the height of the Eiffel Tower. It is visible how the camera glides along the seabed where a specialized subsea wellhead is installed. This equipment functions as a giant valve to regulate the flow of oil and natural gas. Positioned only a few meters above the ocean floor, the wellhead must withstand physical pressures hundreds of times greater than those experienced on the surface of the land. Installation of these components requires near-perfect precision, with tolerances measured in mere inches. Because the deep ocean remains in complete darkness, the work is carried out by remotely operated vehicles, or ROVs. Robotic arms maneuver multi-ton steel components with slow, deliberate movements to connect and seal the pipeline system. Everything only gets more complicated as the extraction network expands. Oil and natural gas flow from the wellhead into a vast network of subsea pipelines. These lines stretch for dozens of kilometers across the uneven terrain of the seabed. Multiple anti-corrosion layers protect the steel from the salt water. Each section is welded to the next and monitored ceaselessly to prevent the development of leaks. The process is only gaining momentum as the resources move toward the surface. Floating fortresses known as floating production, storage, and offloading vessels, or FPSOs, rise above the waves. Unlike fixed platforms, these vessels are not permanently attached to the seabed by rigid legs. Instead, massive steel mooring chains hold them in position, allowing the hull to move in rhythm with the ocean swells while maintaining a stable connection to the systems below. One can notice the slow tilt of the vessel as it adjusts to the environment. One single FPSO vessel has the capacity to store up to 2 million barrels of oil. This allows it to serve as both an initial processing facility and a floating storage unit. Eventually, the crude oil is transferred to long-distance tanker ships for final transport. The equipment moves with a constant mechanical precision during every transfer. From fixed platforms and semi-submersible rigs to subsea wellheads and vast underwater pipeline networks, every element forms a single continuous extraction chain. This system stretches from deep beneath the Earth to the surface of the ocean. It transforms energy buried for millions of years into the fuel that powers the modern world. The material leaves the extraction site, transitioning into a calm stage of global distribution. $100 million is the maximum cost for a single exploratory well drilled in the open ocean. Why invest such a massive sum into a hole in the seabed before knowing if anything lies beneath? The geological maps created through surface surveys only provide a probability of success, but the physical presence of hydrocarbons can only be verified through direct penetration of the Earth. Engineers on the decks of specialized survey vessels lower massive acoustic transmitters directly into the water column. These devices emit powerful sound waves that travel through the depths to hit the seafloor and the layers of rock below. The waves bounce back and are captured by an expansive network of surface sensors. This process generates a three-dimensional seismic map that reveals sedimentary structures where gas and oil have been trapped for millions of years. But this is just the beginning. A drilling platform is towed to the precise coordinates identified by the data. On the main deck, hundreds of steel pipes, each measuring 9 meters in length, are connected sequentially. One can notice how the hydraulic arms move with mechanical precision to build a massive drilling assembly that descends through the ocean water and enters the underground rock formations. It gets more complex further on. At the very tip of this assembly sits a drill bit equipped with cutters made of a super hard alloy. The equipment gradually grinds through the solid rock via continuous rotation under extreme pressure. After the drill reaches the target depth, the team sends a monitoring device known as a logging instrument down into the borehole. Hidden in complete darkness deep beneath the seabed, this tool releases electrical signals, sound waves, and gamma radiation into the surrounding geological layers. The process is only gaining momentum. The returning signals travel back to the surface as streams of data. These readouts show rock porosity, fluid flow capacity, and the actual reservoir pressure within the stone. These measurements ultimately determine whether the well, which costs between $50 million and $100 million, becomes a productive field or is permanently abandoned as a dry hole. It only looks obvious to extract the resource, but in reality, the hidden pressure of the Earth creates a constant state of danger. If operations are poorly managed, the reservoir pressure can suddenly surge upward through the pipe, triggering a blowout. Crude oil escaping from the seabed at such force can devastate marine ecosystems for decades. The cleanup and containment of such environmental disasters can cost several $billion. Every stage of the process must be strictly controlled with zero tolerance for error. One can notice how automated valves and pressure sensors monitor the flow at every second of the operation. Even the smallest mistake can turn an ambitious energy project into a global catastrophe. Thus, the data continues to flow to the surface and the well is secured before the next phase of extraction begins. 100% of offshore drilling operations are accompanied by a state of constant, calculated risk. Why must engineers maintain such extreme vigilance during the drilling phase? Drilling into the Earth's crust releases immense forces that have been contained for millions of years. If the management of these operations falters, the internal reservoir pressure can surge upward with violent force, triggering a catastrophic blowout. The process is only gaining momentum. Crude oil escaping directly from the seabed has the power to devastate entire marine ecosystems, resulting in environmental disasters that require billions of dollars to contain and remediate. One can notice how every single stage of the extraction process is subjected to total, uncompromising control, because even a microscopic technical mistake can transform a high-budget, ambitious project into a global ecological catastrophe. It only looks obvious that the work becomes easier once the well is secured, but in reality, this is merely the transition to the extraction phase. At the beginning of the cycle, natural underground pressure serves as the primary engine, forcing oil and gas upward through the narrow channels of the production tubing. But this is just the beginning. Over a period of months or years, the natural reservoir pressure inevitably declines, which renders the installation of artificial lift systems an absolute necessity. These mechanisms include electric submersible pumps, which are capable of producing up to 20,000 barrels of fluid per day, or gas lift injection systems designed to maintain a stable and predictable flow. What reaches the surface is not a finished product, but a raw, turbulent mixture of crude oil, gas, water, and fine sand. At the production site, the camera glides along the complex piping where this stream enters multi-stage separators. The equipment gradually separates the gaseous phase, which is then compressed for export or re-injected back into the reservoir to sustain internal pressure. Simultaneously, the extracted water undergoes rigorous treatment to remove residual oil and solids before being discharged back into the sea under the mandate of strict environmental regulations. Everything only gets more complicated as the crude oil undergoes secondary processing to strip away corrosive salts and mineral impurities. One can notice the metal tanks where the cleaned oil is transferred for temporary storage. Throughout every meter of the facility, thousands of specialized sensors continuously monitor the pressure, the temperature, and the specific flow rates. It seems simple to watch a gauge, but in reality, modern offshore platforms transmit this data in real time via satellite to onshore control centers located hundreds of kilometers away. This allows for immediate remote intervention the moment any irregularity is detected by the system. If automated sensors identify a sudden drop in pressure or abnormal flow conditions, they trigger immediate alarms and can autonomously shut down the entire well to prevent a mechanical failure. Offshore oil production operates as a tightly synchronized chain, stretching from initial flow management and phase separation to chemical treatment and storage. This stage of the industrial cycle requires extreme precision, as a minor error can result in financial losses exceeding millions of dollars and cause irreparable damage to the surrounding marine environment. Transportation to the shore represents the next logistical level. In oil fields located in closer proximity to the coastline, subsea pipelines stretching for dozens of kilometers carry the raw material directly to land-based refineries. In deeper offshore fields located far from the mainland, the crude oil is instead transferred onto specialized tanker ships or floating storage units. Each of these massive vessels is capable of transporting several million barrels across the ocean. From this point, the energy resource that required millions of years to form begins its final journey toward the refineries and eventually into the infrastructure of daily human life. The industrial sequence of installing subsea pipelines and offshore rigs concludes here, having transformed a geological anomaly into a refined global commodity. The material has been successfully extracted and moved toward its final destination, completing this phase of the production cycle.